Start recording. So RAID stands for Redundant Array of Inexpensive Disks or Independent Disks. You create an array of disks and stitch them together to enhance the size and resilience and performance criteria of disk I/O, right? So it's a special topic when it comes to disk I/O. And you team those together. If you were using a 4K movie and storing it on a RAID 0 array, this is called disk striping. Half of the movie would be, or half of the first chapter of the movie would be on sector A. The other half of chapter 1 would be on sector B. And when you get to chapter 2 of the movie, the first half of the chapter 2 is in disk sector C on the first disk drive. The second half of chapter 2 is on disk 2. So I'm oversimplifying here, but basically you split the data up into chunks and they each work in tandem to double the performance. So whenever you stripe, if you have a RAID 0 stripe with 3 disks, it's triple the performance. A RAID 0 disk array with 4 disks, it's 4 times the performance, read and write. If you have a RAID 0 array with 5 disks, it's 5 times the performance. You start approaching like almost RAM quality performance, right? So you keep doing that. I hope this rings a bell. The other benefit is that you're balancing the load of disk reads and writes. So you tend to extend the shelf life of disks. If you're splitting the load of disk reads and writes across 4 or 5 disks, you tend to have a quarter to a fifth of the wear and tear. Does that make sense?
Yeah.
Yeah. And then disk mirrors, you have exact duplicates. So when you're working RAID 1, you're storing identical copies. So you still get some load balancing when they're reading the disk out, when the data is being read out of the disks. The disks can work in tandem when data is coming off the disk spindles, right? But when you're writing to a RAID 1 array, you have to write 2 copies, one on each disk. So the write operations tend to be halved or quartered or an eighth. You also have to have even numbers of disks. So one of the differences between RAID 0 is that you can have any number of disks that are striped. In RAID 1, you have to have even numbers of disks, 2 or 4, 6 or 8. You need to have even numbers of disks, but the write performance is halved, right? A hybrid approach is RAID 1.0, where you put both of them together, you stripe them, and you have an extra copy, so it's mirrored and striped. So RAID 1.0 is called mirrored stripe or striped mirrored, and basically you get the greatest performance and greatest fault tolerance. The only difference is that half of your disks, because they're mirrored, if you have 16 disks, you're really only using the equivalent of 8 disks. So the downside of having 1.0 is that a lot of people consider that it wastes disks. When you're running virtual machines in a server environment, this is the way to go. Now, there are other RAID models. There's one called RAID 5. It's a poor man's RAID 1.0. There's parity and recoverability, but there's some multiple copies, but it's done with some algorithms. So there's a software layer with an algorithm, and it takes a lot of overhead. So you get most of the capacity of your disks, unlike 1.0. But the problem is that you take a performance hit. And if you lose any one disk, you're kind of screwed. So, and of course, now they have RAID 5.0, which are mirrored RAID 5 arrays, RAID 6, which are 2 extra parity disks, and then RAID 6.0. There's all these weird things that manufacturers are doing. The basics are all that we need to understand here for disk I/O. And as a specialty topic, you want to take some time to read the rest of this to refresh your memory from CSE 241. And this explains RAID 5. So you basically get some of the benefits of RAID 1 and some of the benefits of RAID 0, but it's a poor man's approach. The people do RAID 5 when they need most of their disk capacity and they can't afford to lose the capacity for half of the disks that are in the array. So RAID 1.0 uses the most disks, but the performance benefits and redundancy are amazing, just plain amazing. So if you ever need to have a lot of disk storage and you have a budget where you can do this, you also want to run virtual hard disks on a RAID 1.0 array. You never, ever, ever want to use RAID 5 for VHDs, for virtual hard disks. It's just too slow. It's terrible because RAID arrays are often connected across a network. So you also have a network backend that has to be high performance. That's not true for every RAID configuration. Many RAID configurations are connected on the backside through a disk controller that's part of a server expansion slot on a motherboard. So you have direct attached storage. Then you have RAID arrays that are in a powered platform where it's just the disks and there's a small microprocessor. And those are standalone and those are connected across a network. And it's common to bind gigabit Ethernet channels into 2 and 4 and 8 gig multi-channel. It's called Ether channel. You bind the Ethernet ports together so you get 2, 4, or 8 gigabits of network performance. And so those separate devices are often used to create network attached storage, which is called NAS, or SAN, storage area networks. Has anyone ever heard the terms SAN or NAS?
Yeah.
Okay. So we go into that detail here. We talk about, okay, if you have a chassis and it's connected directly to a server motherboard through a dedicated disk controller with buffered memory, then those disk read writes are protected even if the power goes off. They're buffered in memory. The disk interface that's most common for servers is called SCSI. There's a new implementation of SCSI that works across serial instead of parallel. So SCSI was traditionally a parallel. You couldn't have a cable that was longer than so many 2 or 3 feet because you'd have 1632 or 64-bit. You'd have 64 wires and it was a parallel connection. Now they have serial attached SCSI. They figured out a way to kind of flip this on its head. Serial attached storage can work across greater distances and all the data flows very high burst, very high speed, serial connections. So everybody understands the difference between parallel and series, right? Parallel and series? Yes, no, maybe?
Yep. Yeah.
Okay. So network attached storage is the older version of the network disk array. So if you have massive arrays and they're not directly attached to a server, then that storage is accessible on the file system level. Storage through a SAN, a storage area network, is accessible as if it were a disk connected to the server. It's a block level access. So one thing to understand is that NAS data access for disk arrays is available across a network with file level access. That means you're using some kind of file system, NTFS, FAT. You're using it presents to a client where they have to speak the same file system language. Storage area networks, because they're available on the block level, it's block or sector level access. It's block level access. That's on the hardware layer. So when it is presented to a host or a system for use, it appears to be a disk, like an unformatted disk. And you choose how you want to use it. You can boot from a SAN disk. You cannot boot from a NAS disk. Let me say that again. You can have a diskless server that has no hard disks, and you can boot that server with the logical unit. All right, so when a NAS or a SAN are prepared for use, something called a LUN, it's spelled LUN, but it's pronounced LUN, is created. And in a SAN, it works like a hardware disk. So it's block level. It's just like a disk sector on a physical hard disk. So the NAS provides file level data stores. Your server would have to boot into the operating system and then translate to some kind of file system like NTFS or ext4 for Linux, or in the Apple world, it's APFS. You have the advanced performance file system in Apple's, or AFS Plus. You'd have to have the server boot into some kind of operating system before it could access file level data stores. Okay. So NAS data information, you cannot boot a server using NAS, but you can have a huge SAN. By huge, I mean like this. Then you can have another rack with nothing but blade servers, meaning it's just the CPU and memory. You can have 4 or 8 servers in a single rack element like this. And each of those 8 servers is using a high-speed network connection with a SAN, a storage area network. The storage area network can be clustered, or there can be a redundant copy. So you could have one here and one there. If this side fails or blows up, the other one keeps going. There are mirrored copies on each. The servers don't know any different. They just think that they're still connected to the same hard disk. So this is incredibly powerful, but also very expensive technology. So you can go from very simple things. Now, one aspect, I'm not sure I ever shared this with you, and here, if you have Windows 10 or 11 Professional Edition or Education Edition, you can create a software level, or you can create 2 volumes, and you can create a RAID 0 or a RAID 1. You can stitch 2 logical volumes together on the software level using Disk Manager. So there's hardware level RAID with hardware dedicated disk controllers for disk attached storage, NAS storage, and SAN storage. But you have servers and clients that are capable of creating redundant disk arrays in software. So if I had another physical hard disk here, I could split it up into 2 volumes. I could stitch them together so they work in tandem and do RAID 0. The only difference is, because I'm doing it in software, there's some overhead associated with software. There's very little overhead associated with hardware. So if you really want to do RAID and your concern is high performance, you want to run hardware with dedicated hardware controllers. That's the basics. Whenever you see a link like this, you do want to click on this, but we are talking about huge amounts of information. This, by the way, this stuff right here and a storage area network is the hardware level that allows AWS to operate. Did you know that Amazon has a data center like the one we just showed you? They're running SANs in that data center. And if you walk into an AWS data center for Amazon, you'll see stuff like this. And most of it will be running storage area networks. And those storage area networks are connected through the back end to the cloud. And that's why you can stand up a virtual machine so quickly with AWS. It's using SAN technology on the hardware level. And in order for that to work properly, the server operating systems have to be able to speak a SAN language like iSCSI. So iSCSI is a special network protocol that allows a SAN to work. And it's really important to understand that before that time, SANs were around. NAS has been around for 30, 40 years. SANs have been around for about 20 years. But SANs weren't affordable or practical for the first 10 years because they used fiber connections between disks. Now you can use plain Ethernet. So you can use very cost-effective, very low-cost Ethernet. And how many of you know you can get on Amazon right now and order like a 10 gig switch for 180 bucks? Meaning each port has 10 gigabytes of speed. Anybody? Did you know? Did we lose somebody? We lost somebody. Oh, we lost Tommy. All right. Well, maybe he'll pop back in again. In any case, any questions about disk I/O, enhanced disk I/O, special methods to enhance disk I/O? All right, going once, going twice. Okay, so let's just walk through some of this for about 10 minutes, and then I'd like to stop and talk about AWS. So essentially in chapter 11, it talks about disk I/O. And of course, that's an important topic because when you look at the von Neumann diagram, basically everything that we've covered so far has to do with when you talk about what are the three qualities every operating system has to have? The three main functions. Let's use a little bit of our study day right now. Chapter 1, Module 1. What are the three easy pieces of an operating system? What are the three essential functions of every operating system, or it wouldn't work at all as an operating system? Hello? Did I'll give you a hint. We've been working with virtual machines. But long before that virtual machines were popular, an OS was called the virtual machine, right? So virtualization is one of the things that an operating system, one of the main functions of an operating system. What's the other one? Starts with a C. Anybody?
Concurrency.
Concurrency is correct. And now we're talking about disk I/O and file system, and that has to do with the last or final quality of an operating system. It's a P word. What's the word? Persistence, right? You have to have non-volatile memory, right? Everybody with me? Okay. Most disk I/O happens across the south bridge of a motherboard. In terms of data bus, that's not the high performance side. If you have a direct hard disk controller that's connected through the north bridge, that's high performance. But typically, input output with disk is way slower. There's a huge overhead, huge performance hit in terms of immediate access for the data to memory and CPU. So that's one of the dynamics that we have to take into account, right? Is that you have much greater distance from the CPU and RAM, and it's usually across the low performance data bus. It's not the front side bus or north bridge, it's the south bridge. This business about plug and play. Most everybody does not have to mount a hard disk in Windows or in a Mac OS environment in order to use a USB, correct? But in Linux, you often have to mount a disk. You have to intentionally connect to that hardware level in order to be able to access anything that has to do with the disk. So in the Linux world, a lot of things don't work automatically. You have to first mount a disk or attach a disk. Everybody's heard that term before, right? Mounting a disk.
Yeah.
Okay. What I wanted to do was to kind of walk through the steps for preparing a disk for storage. So when you have a physical disk and we're talking about layer one, the hardware, a good way to think of it is that a disk is like a field. It's a piece of farmland, and let's say that a farmer sells the farmland. Everybody with me? Have we ever had this? Have we ever walked through this before? Anybody remember how a physical disk is like a field a farmer sells?
Sounds familiar.
Yeah, so we have a field that a farmer sold, and let's say that the farmer sells the farmland, a huge field, to a business entrepreneur who's very wealthy, who wants to start his own sporting complex, and he wants to have different stadiums with different fields. So he wants to have a baseball field, a football field, a soccer field, and so on, right? So let's pretend for a moment that it's very large and it's raw. Some of it had crops on it, some of it was wooded. There were ponds and dirt roads. And so this developer decides they're going to bulldoze the whole thing, right? They're going to bulldoze the whole thing. When they bulldoze it flat, so it's flat before they lay out the boundaries, that's called initializing a disk, right? So to use an analogy, if a physical disk were like a large farmer's field with all sorts of landscape features, in order to make it usable, you'd have to level it, you'd have to make it consistent, you'd have to flatten everything so it's smooth. And you'd have to do that for the buildings you build, for the sports fields you lay out, and for the parking lots for all your fans, right? Your sports fans. So you'd have to do that. That's initializing the disk. Once it's initialized, you lay out boundaries, main boundaries for each sports field, for the parking lots. Those are called partitions. When you lay out the major boundaries, those are called partitions. And a disk has to have a partition before it can be usable. You have to have basic boundaries. And then within the partition, you create an index where you can set up disk sectors to store the actual data. That's called formatting. So once you've laid out the main boundaries of a usable disk, this often establishes something called a logical volume. And yes, in servers, you hear the term LUN, right? So LUN as an acronym. When a partition is created, it's a portion of the physical disk. It's not the entire physical disk. This is something that often confuses people because, like right here, you'll notice here is my C drive partition. It's 200 and everybody can see this? Yeah.
Yeah.
Okay, so I have 236.95 gigabytes. That boundary, the outer boundary of this is a partition for NTFS. And then inside here, it's formatted into so many disk allocation units or sectors. And that creates a logical volume, but the entire disk itself is much bigger. And there are other partitions that are established that are not accessible directly through the operating system because they're intended to boot the thing. There's a new convention called UEFI where there's a hidden disk partition and the power on self-test and BIOS data is actually stored on a hidden disk partition as opposed to a EEPROM rewritable chip. That's because hackers have figured out a way to store all kinds of malware on the chip. So if they hide a disk partition and make it inaccessible to all but world-class hackers, then you can store the boot information for a system in a hidden partition. So in this case, on my laptop, you see I have a physical hard disk that is 238.47 gigabytes large as initialized, but there are 3 separate partitions, one of which was formatted to be the C drive. And in Windows, when you're using NTFS or DOS, they use drive letters. In the Linux and Mac world, we don't use a drive letter. We just use a slash to represent the root or beginning of the file system, okay? Which should be pretty much review for most. Any questions about preparing? Now, the main boot record is what actually is used when a disk is designated, if the partition is designated a primary partition. So you have all these partitions on a physical disk. There's a partition table that organizes the primary information for that disk I/O. So you can have a traditional legacy MBR, or you can have a GUID ID partition table, which is the current and enhanced version of a partition table. If you have disks that are larger than 2 terabytes, you often have to establish a GPT partition when you initialize the disk instead of an MBR partition. So MBR is like the old school way of doing things with DOS and older versions of Windows. And there's a size limitation, right? So with GPT, the newer partitioning convention, you can have very large disks and very large disk arrays. Any questions about partition tables and how partition tables organize? They're basically used to store the essential attributes, and you can't have a functioning partition without a valid partition table. So this is old school MBR, main boot record. Either way, if you have MBR or GPT, one of the partitions is designated a boot partition. And then all the rest are designated extended partitions. This is in the NTFS file system or Windows world of things. So when you're preparing disk I/O, one of the partitions is listed as a primary, right? See how it says primary at the end of that pop-up right here? Right there, it says primary. If I hold a pointer over this, usually the other ones, well, a lot of times when you have a large disk and you set up separate partitions, once the first partition is designated a primary, the rest are usually considered to be extended partitions. Now, a system partition, the one that's hidden, because this is used for troubleshooting boot problems, it's also bootable, which is why it's a primary partition. An enhanced partition, an extended partition is not a bootable partition. So in order for a partition to be considered bootable, it has to have a primary partition. That's just additional information for your own edification. There's another view. Oftentimes you want to make changes to disk partitions and you can't. There is a command prompt. You can do this in PowerShell, but there is a command prompt that you can run with administrative access to a command prompt. It's called diskpart, and you can basically take a command. Now, and then issue the command, and then if you want to know how to use it, you can just have a /? So list disk, list partition, list volume, list virtual disks. So we can attach virtual disks as if we can take some disk space, create a virtual disk in computer management with disk management. We can create a virtual disk, then we can attach it, and it'll behave as if it were a physical disk, which is kind of nice. There's all sorts of neat things we can do. You may remember something about this from the forensics class where we created like a small VHD and pretended it was a USB drive. Does everybody remember that?
Yeah.
I do.
So I'm going to do that now. And I'm going to create a VHD, and I will use VHDX, and I'll use a fixed size instead of a dynamic size. And I'll create it in my temp folder on my C drive. And so I'll create this as, let's call this other data, right? And I'll call this drive letter D. Or yeah, drive letter D, because I don't have a drive letter D. And I'll put a -D because that'll help me remember the drive letter I want to assign to it. Now, if I were doing elegant things and providing disk access for special purposes, I could have a drive letter F for finance. Now let's make this a little more interesting. Let's say this is money data, okay? Drive letter F for finance. I'm going to do this. I don't want this to be very large, so I'll make it 2048 megabytes, which will make it 2 gigs. And when I partition it, it's going to take up some additional space to organize the partition table. So that's another thing. So that I don't get the full, that's another thing you have to realize is that there's overhead for the partition table. So if I want this to be a full 2 gigs, I should actually put in a little more. So I'm going to go ahead and put in like 256 more than the 2048 to make sure I get a full gigabyte. So 2048 plus 256 megabytes would be 2304. And I'll go ahead and say okay. And you'll see down here, it doesn't take long at all with a solid state hard drive. As soon as this is finished, I can basically use diskpart to see it, or if I attach it, right? So I'd have to attach it, and if I attach it, then it'll actually show up in diskpart when I list virtual disks or disks. I can see it in computer management here you see 2.25. It's not initialized. I can initialize the disk. I can choose MBR old school, or I can go GPT if I want to do advanced things like stitching them together in software and so on. There are previous and older versions of Windows that don't talk GPT, so that's an important thing. If you're using legacy or old Windows, you have to go MBR instead of GUID partition table. So GPT stands for GUID, graphical unit identifier, right? GUID. I'm going to go ahead and put GPT on it because I'm going to be using, and now I have a partition. So I've initialized it. Now I don't have a partition. I've initialized it so that it's capable of receiving a partition using a GPT format. And now I can create a simple volume, which will establish the partition and format the disk. I'm going to use drive letter F. And I'm also going to choose the size. I can leave the allocation unit size. This is the logical layer of disk sectors. If I choose a larger allocation unit, like if I have a very large VHD, I can store virtual machine disk partitions and load virtual machines that much faster if I use a 2 megabyte allocation unit. If I have a lot of standard if I have a lot of very small files because I'm using it as a log storage for very small text files, I might want to use a very small 512 kilobyte allocation unit size instead of megabyte. And that would allow me to more efficiently store smaller text files. If I use the default, it'll use 4096. So if I have a 30 kilobyte log file, I'm wasting 4,066 kilobytes because I'm only storing a 33 kilobyte file in there. Does that make sense? So you get trade-offs with efficiency. If you're loading large media files or large data files, you can go with an allocation unit size that's much larger. If the purpose for the disk store is to collect and organize lots of smaller text or data files, you'd want to format it with a smaller allocation unit size. In Linux, does anyone know what the equivalent of an allocation unit size is in Linux? Anyone? Does the term inode sound familiar? Inode? Okay, maybe not.
Yeah, for me.
Yeah, I'm gonna accept the default and I'm gonna call this money data, right? Just so it's consistent. And I'll take the perform a quick format off and then hit next and then finished. And then after it's finished, because I've designated a drive letter, it'll attach this automatically. It will attach this automatically as a logical volume. And now when I open up my file manager, right? There we have it. I have a little bit more because I wanted to be sure I had at least 2 gigs. And in case there were other partitions. Any questions about basic physical disk preparation as a part of disk I/O interests? Okay.
No, for me.
I'm going to stop sharing and stop recording.